object at a certain interval of time, average speed is somehow across the total distance. Whenever you're talking about the average speed, it would always be total distance upon the total time taken. And then if you're talking about the instantaneous speed, remember that whenever there is an instantaneous speed on the cards, you need to keep the time interval as small as possible. And instantaneous speed would get to be the change in the distance upon the change in the time as well. Now, the basic thing is, I'm pretty sure that all of you knows about the position, these thing is. If I'm talking about uniform or variable speed or instantaneous speed or average speed. But there are some questions where students often mess up. Now, for example, if somebody is asking you that the body is moving with the uniform speed, so what is going to be the relationship between the instantaneous speed and the average speed? G, any one of you? G, we've got Alia first of all. G, Alia, Arshit, what do you think is going to be the relationship between the instantaneous speed and average speed if a body is moving with the constant speed? Yeah.
Would it be the same, I guess?
Exactly. They have to be the same, right? If you're talking about the uniform speed, at the uniform speed, one thing is for sure, that the average velocity or the speed, if you're talking about, that should be equal to the instantaneous speed. Now, the thing is that how do you calculate the instantaneous velocity or the average velocity? For example, if you guys got some sort of a distance time graph, Now, this is a very common mistake as well. If you've got a distance time graph, everybody knows that from the distance time graph, the gradient of that curve is going to be the speed. But there are multiple ways to calculate the gradient. And to have that much of an accuracy, we need to calculate gradient in many different ways. Either you guys can simply do the change in y upon the change in x point. Now, for example, if I'm calculating the speed, and the speed could be either the instantaneous one or the average speed one, right? For the average speed, what coordinates you'll be picking up, Hassan? If you're calculating the average speed from the distance time graph, what coordinates you think you should be picking up?
The gradient.
Well, but there are multiple ways to calculate the gradient. Would you be calculating any 2 points, or to have that much of an accuracy, you'll be calculating some particular points?
Tangent.
No. For average speed, remember that whenever you calculate the gradient, it has to be the very initial point, or maybe the origin, versus the final point. Got that? Where the curve terminates. Got that? And whenever you guys are talking about the instantaneous speed, we'll probably do it with the help of a tangent at that point. Got the difference? Right? So it is preferred to calculate the instantaneous velocity by drawing a tangent on that curve. And it is preferable to calculate the average velocity by just taking the initial and the final point on the curve. I hope you guys got that, right? Now, talking about these thingies, now there are some important points about acceleration as well. I'm pretty sure everybody of you knows how to calculate the acceleration, right? But for example, if a body is revolving in some sort of if a body is revolving in a circular path, would body ever be having some sort of acceleration, first of all? Gee, we've got Amy Hart. If a body is revolving in a circular path, do you think we'll ever be having some sort of acceleration? With a constant speed as well. Okay, and why so? If the body is moving with constant speed, why would we be having some sort of acceleration? Yeah, it is centripetal acceleration, yeah. I know there is centripetal acceleration, but how do you think that in a circular path we would be having acceleration? Asat,
Due to the velocity being a constant.
well, velocity is being constant. And don't you think that whenever the velocity is constant, acceleration is supposed to be zero?
Yes.
So why do we have acceleration in a circular path?
I'm not quite sure.
Ji, Ariba. It's exactly, I mean. So it is constantly changing its direction. Got that? So even though it got some sort of constant speed, it is continuously changing its direction. And what is the direction of the velocity when an object is revolving in a circular path? That is a tangent to that point. Got that? So that is how we should be talking about all these terminologies. You know, you're good with the definitions, but for the Cambridge students, remember, you can be asked about the definition of acceleration or the speed or the velocity and their units as well. For Edexcel, we are never being asked about the definitions, right? So that is what we need to know about the basic terminologies. Now, the next topic is a bit more important, and that is mainly about the graphs, the motion graphs. So first of all, you know, we have got the displacement time graphs. And whenever you're talking about the displacement time graphs, there is one thing for sure, which everybody should know, that for a displacement time graph, you can calculate the distance, sorry, we can calculate the speed by just calculating the gradient. We just talked about it. Gradient of a dt curve would always be getting you the speed or the velocity. And I've already talked about one thing, that, you know, speed can be, you know, he can ask you about different speeds. It can either be the instantaneous speed or it can either be the average speed. So I hope all of you get to understand that whenever you're talking about the instantaneous speed, it is better to draw a tangent. It is better to calculate the gradient with the help of a tangent at that particular point, because instantaneous velocity is a very particularized velocity. You've got a certain time, and that is the time you're talking about. Okay, who's texting? Change in direction. Exactly. Ale. So after that, we've got the average velocity. And whenever you guys are talking about the average velocity, it is better to calculate the average velocity by taking the initial and the final points. But, you know, everybody gets to understand this thing, you know, they can easily calculate the gradient. But the important question is that, for example, whenever you guys are given with the displacement time graph, you know, let me talk about a displacement time graph. For example, you've got a graph of an object that looks like this. You've got a straight curve over here. You've got distance and time over here. The curve gets constant, and then it decreases somehow like this, only to increase like that. First of all, can anybody explain the type of motion this object is having right now? If this is a displacement time graph of that object? Okay, we've got Bilal as well. Ji Bilal. Can you explain the type of motion we're having over here right now? Ji, Jasmeet, what do you think about it? If you've got a displacement time graph like this, what is going to be the object? Well, the body is accelerating, that is for sure. But Bilal, how it is accelerating, you need to explain. For example, you've got the curve from here to here, right? What can you say about the, you know, acceleration of, what can you say about the velocity of an object in this instant from O to A? Yeah, it is increasing. And at that point, the velocity is somehow 0. right? Because the distance is constant, the velocity has to be 0. Over here, the velocity would be increasing. Over here in this curve from point B to point uniform acceleration, constant velocity, uniform deceleration, and acceleration again. Exactly, Ariba. That is the way. A, B, C. Okay, you've got C and you've got D over here. Now from this graph, from the displacement time graph, how would you get the acceleration time graph? G, Hassan? This is the displacement time graph. How would you get, what is going to be the shape of the acceleration time graph from here? G, Hassan? Could it be a straight across and change altitudes? Well, somehow it is going to change altitudes, but how? G, can anyone explain? Whenever you're talking about the acceleration time graph from here, first of all, this is over here, we've got acceleration, and over here, we've got the time. So first of all, look into this curve. In this part of the curve, the velocity of a body is somehow constantly increasing, right? If the velocity is constantly increasing, what is going to be the acceleration at that instant of time? Exactly, Jasmeet. It is going to be somehow 0 like this, right? But right after reaching at point A from B, where the velocity of the object was 0, would it be having some sort of acceleration? Yes, it would be having some sort of a drop like this, right? So the point here is that by talking about, from time over here, the thing is that you can calculate the gradients, you can calculate the velocity over here, and from velocity, you can take a guess about the acceleration, right? So the curve should have been somehow, for this instant of time, you can see that the body would be having a decreasing acceleration, then it must increase like this at a constant rate to get to 0 again. And for the same instant of time, it would get to 0 as well. So that is how you can draw acceleration time graph from the distance time graph. If you guys got any questions from this part, you can ask by using your mics or the chat box. That's fine with me. Come on, I'm just testing you guys. You guys need to be a bit quicker. Okay, that's fine.
Yeah, I have no
So,
questions.
okay, that's fine. So after that, we've got the speed time graphs. And there are only two things that we can calculate from the speed time graphs. The one important thing is that whenever you're talking about the distance from the speed time graph would always be the area under the curve. And whenever, secondly, we're talking about the speed, we just need to remember whenever you're talking about the acceleration would always be the gradient of that certain curve, right? So we've got these two things from the distance and acceleration, but there are some important types of graphs where students often messes up. For example, if he's drawing a graph like this, if this is a graph, if this is some sort of a velocity time graph, right? How would you be able to calculate the distance covered by the body? If this is a velocity time graph, not the speed time graph, remember, direction is important when you talk about the velocity, but direction has nothing to do whenever you talk about the speed. So we have got these two parts of the curve. This is the first one. This is the second one, right? What we're going to do, we can never calculate the area under the graph by just talking about the triangle, the whole triangle under this area, right? We just need to calculate the area under this triangle, the area under this triangle. That would give us the two distances. This is the distance displacement traveled in the upward direction. This is the displacement traveled in the downward direction. We just need to subtract them in the end to get ourselves the final distance, right? And if this would have been the speed, remember, then we can add them up. Got that? So you need to take care that when the graph is the speed time and when the graph is velocity time. If this would have been a velocity time graph, you would have been just subtracting the distances. And if this would have been another student is joining shortly. I said, we cannot do anything. You can join. So we've got the speed time over here, and we've got this part of the graph. So did you guys understand this basic concept? If this is a velocity time graph, you need to subtract these two areas. If this is a speed time graph, you're supposed to add these two areas. Got that? Now we'll get to the next important topic, and that is the basic difference between the scalars and vectors. And I'm pretty sure everybody among you guys knows the difference between the scalars and vectors. Whenever you guys talk about the scalars and vectors, the scalars can only be represented with the help of a magnitude. Whenever you talk about the vectors, it is just talking about the magnitude and the direction. But the important thing is that how you guys would be able to add the magnitudes. That is pretty much easy. जी अमित
सर आपने जो
जी जी
पिछले के अंदर कहा था तो फिर हम लोग को वो हम लोग को आइदर वेलोसिटी टाइम ग्राफ दिया स्पीड टाइम ग्राफ, तो वेलोसिटी टाइम ग्राफ के अंदर ये सब कंफर्म करना चाहा, आप कह रहे हैं कि बोथ एरियाज को सब्ट्रैक्ट करना होगा वेलोसिटी टाइम ग्राफ के अंदर
हाँ
और टाइम ग्राफ के अंदर ऐड करना होगा, वो क्या कहते हैं, टू
exactly
एरियाज को।
yep because speed has nothing to do with the signs or whether the body is moving back or not, but velocity got something to do with the direction as well, right? So
Yes.
while talking about the scalars, I'm pretty sure it is very much easy to add the scalars. Like for example, if you want to add 7 and 2, it can easily be 9, right? But the thing is that we can't really add vectors in a simple way. So adding vectors require a certain thingy. Like for example, if you guys are talking about addition of vectors, you can do this addition of vectors by using the head to tail rule or the parallelogram rule. The important among these two rules, between these two rules, is the head to tail rule. And how do we talk about head to tail rule? For example, if you've got two vectors, one of them is directed like this, the other one is directed like this, and you're just supposed to add them. You need to add A and B. Got that? If you are supposed to add A and B, what you're going to do, you just need to join the tail of the second vector with the head of the first vector. So you'll have two vectors like this. This is going to be A, this is going to be B. Got that? We just need to join the tail of the second vector with the head of the first vector. And this is going to be A and B. And now, at the end of the day, remember the very important thing that the direction of the resultant vector should always be towards the head of the last vector. This is going to be the resultant vector whose, and this is going to be the sum of A and B. But the thing is, the important question from here, which appears in many of these exams, that we just need to draw a scaled vector diagram. We need to draw the scaled vector diagram of any structure given. For example, they might give you a vector having 200 newtons of the magnitude, and they can give you a vector having 500 newtons of the magnitude. And we just need to draw a scaled vector diagram. So first of all, we need some sort of a scale, right? And what scale I'm going to use over here? I've got 100 newtons, and 100 newtons would be equal to 1 centimeters. Got that? So 100 newtons would be equal to 1 centimeters. And I can just simply sketch them up. 200 newtons would be equivalent to 2 centimeters, right? Remember that the magnitude of a vector, whatever vector you're talking about, that is somehow equivalent to its length. Got that? Length is a basic measure whenever you're talking about the magnitude. So if you've got 200 newtons over here, 500 newtons over here, so 200 newtons mean we've got a 2 centimeter line over here. And we just can join the tail of the 500 newtons with this head. So we would have something like this, right? This is going to be 5 centimeter. And then we'll end up finding out the resultant vector, which is going to be something like this, right? If you want to calculate the magnitude of the resultant vector, for example, this is 2 centimeter, this is 5 centimeter, and this line when measured, it comes out to be something like, 5.4 centimeters. So you need to times that 5.4 with 100 to get the final answer in newtons, and that is going to be 540 newtons, right? This is how we calculate the magnitude of the resultant vector graphically, right? Very important question for CIEs. So we've got 540 newtons. But the important question for the Edexcel ones over here is that you're not supposed to calculate the magnitude of the vector graphically. How would you be able to calculate the magnitude of these two vectors? We've got 200 newtons and we've got 500 newtons. And somebody's telling us that whenever we're going to join them, they'll be making an angle of almost like 110 degrees, right? How would you get me the resultant vector's magnitude if these two joining vectors are not perpendicular to each other? Okay, Harry, what do you think about it? How would you be able to calculate the magnitude of the resultant vector not with the help of a graph? Do we have Harry with us? I guess why you guys are so shy about it. Jasmeet, what do you think about it? If you want to join two vectors not perpendicular to each other, how would you get me the resultant vector? Okay. Not sure. Can you explain it again, please? Well, I'm just telling you cosine rule. Yes, I mean, you're fine about it. I'm just telling you guys that you've got 200 newtons over here and we've got 500 newtons over here, right? I just, added them up by using the head to tail rule, right? And if you want a scale diagram, I've drawn the scale diagram as well. I'm just talking about that how you guys would get the resultant vector. And that is going to be with the help of a cosine rule. If this is, this is going to be F1, this is going to be F2, the angle between them is 110 degrees. So you can get the resultant vector by just using this formula. F square equals to F1 square plus F2 square minus 2F1 F2 cos of the angle in between them. Got that? So this is the cosine rule and a very important rule because everybody knows how to calculate the resultant when two vectors are perpendicular to each other, right? But this is the formula where students often get stuck. Okay, what is the question? Well, Asad, why are you telling us cos x is equals to the adjacent over hypotenuse? We can even apply this trigonometric ratio only in the case of a right angle triangle, right? We cannot apply this, cos over here. This is an obtuse triangle. That was the main point, right? So this is how we can add vectors. And this is how we can get the resultant vectors by using these two formulas. Now, for example, this was the case when we're dealing with the non-perpendicular forces, right? Or vectors. But now let's talk about the next case when two vectors are perpendicular to each other, right?
सर
जी.
वो सिर्फ फॉर्मूला कॉपी कर लो वो सर मैं कर
I'll send the sheets in the end. Don't worry about that. Just try to understand as much as you guys can. Okay. So now we've got the perpendicular forces or perpendicular vectors. We've got two vectors which are totally perpendicular to each other. Now, for example, you've got a vector A over here and we've got a vector B over here, right? And you want to just add them up. How can we add them up? By just using the head to tail rule. I'm just going to draw A again, and then I'm going to pick this B up and I'm going to join, and I'm going to join the tail of this vector with the head of this vector, right? So I've got this A over here, I've got this B over here, and the resultant vector is going to be somehow like this. This is, let it be FA, this is going to be FB, and this is going to be F. Now you can easily calculate the magnitude of F by just applying, Yes, Amy? Either you guys can just speak through your mic or the chat box, but that needs to be a bit quicker. Okay, sorry, can you repeat? I'm just asking you if you've got the FA and FB over here, for example, whatever the magnitude of FA is, whatever the magnitude of FB is, how would you talk about F? Exactly, Bilal. We're going to apply the Pythagoras theorem over here, right? We're just going to apply the Pythagoras theorem. So that is just going to be F square equals to FA square plus FB square. And if somebody's asking you about the direction of this F, which is, you need to read the whole question. If it's asking you about the direction with the vertical, you're concerned about this angle. If he's asking you about the direction of the force with respect to the vertical, you are supposed to be calculating this angle. So if you need this angle, you can just simply use tangent theta equals to the opposite upon the adjacent. So FB upon FA, and theta comes out to be tan inverse of FB upon FA. That is how you guys are going to talk about this theta. And that was the case of the perpendicular vectors. So we have talked about two cases. How can we add the non-perpendicular vectors? And how can we add the perpendicular vectors? And how can we do it on the graph paper as well? The third type of questions which we often get from these forces are the free body diagrams. Free body diagrams. And the common problems with the students' answers about the free body diagram is how do they draw vectors, right? For example, there is an object falling down, right? Every one of us knows that there is a downward force acting on this object, and that is going to be the weight, right? And there are two upward forces acting on it. One of them is going to, for example, let it be falling through a liquid. The upward force should be the upthrust, and the other upward force should be the drag of the liquid, right? But nobody among us even tries to figure out that if this object is moving with the terminal velocity, the length of the vector W should be equal to the length of the vectors upthrust and the drag. Then, for example, if the length of this vector is somehow 2 centimeters, the length of the upthrust vector should be 1 centimeter, and the drag should be 1 centimeter as well. Got that? So their length should be equivalent as well if it is moving with the terminal velocity. Or if somebody is telling you just that the object is just moving up. For example, the object is moving up. It is falling through the liquid, but somehow it starts floating. So again, you need to draw the same weight, same upthrust, and same drag. But in this case, if the length of the weight's vector is 2 centimeters, the length of these two vectors must be greater than this 2 centimeters. For example, if this is 1, this has to be 2 centimeters. Got that? So whenever you're drawing the free body diagram of any object, for example, you've got an object that is sliding down a slope over here, right? How many forces are acting on this object right now, Ariba? Okay. If you guys got any question, you can even stop me, right? So in exam, sir, do we have the... Exactly, Bilal. Whenever you talk about the exams, you have to draw the diagram by scale for the free body diagrams, right? So Ariba, I was asking you if you've got an object that is, moving down the slope, how many forces are acting on this object right now? जी Ahmed bole. Exactly,
Sir, I
there is
just
friction,
want to
Harry.
yes, sir, I just want to ask the question that फ्री बॉडी डायग्राम के अंदर हम लोगों को जो है वो उससे ड्रॉ करना होगा बाय स्केल, लेकिन सर वो हम लोग स्केल किस तरह से मालूम करेंगे, वो हम लोग को क्वेश्चन में बताए हुए
Well,
होंगे
you don't
क्या?
need to. You don't need any scale. You just need to, make sure that you show them that the sum of the lengths of the upward vectors should be equal to this one. I've just given you guys an example. It is 2 centimeters. For you guys, it could be 5 centimeters as well. But you need to draw the upward vectors accordingly. Got that?
Okay.
Okay, Harry. So you're telling me that we have got friction and weight and the normal reaction. Exactly. We've got these three forces. One of them should be the friction. If it is sliding down, the friction must be acting upwards, right? And if you talk about the weight must be acting right over here. And the normal contact force must be acting over here. Got that? So this is going to be the diagrams or the free body diagrams that we should talk about. weight, friction, and the normal reaction force. So Reba, this is not the reaction, normal reaction. So these are the things that we need to talk about, the adding forces. Got that? After addition of the forces, we need to understand that how can we resolve them as well, right? So the next topic is the resolution of forces. Student keeps on asking one simple question every time. We do any problem in moments, in in moments, in or addition of the forces, even in electricity as well, blah, blah, blah. Whenever you guys need to deal with the tension or something like that, right? Okay. I said there would not be any tension because the object is not attached to any sort of a string, right? If I would have been attaching this object with the help of a pulley over here, only in that case, there would have been a tension upwards. Got that?
Got it.
So object is moving just freely down. Okay.
Yes.
So you've got the resolution of the forces now, and we need to understand that how can we resolve the forces. So first of all, remember, you already know that if you have got two forces which are acted perpendicular, which were acting perpendicularly upon each other, you can easily calculate the resultant force by just using F. We've got Fx over here, we've got Fy over here. So from here, everybody among us know that Fx must be equal to F cos theta and Fy must be equal to F sine theta. Got that? So we have got this sort of a thing is, Fx could be F cos theta, Fy could be F sine theta. But the problem is that whenever you guys are given with the problems having a slope, for example, you've got a slope over here, right? And you've got an object over here, right? And now there are some forces acting on this object. There must have been a normal reaction. There must have been some sort of a friction. There must have been some sort of a weight as well, right? This is going to be the tension. This is going to be the weight. This is going to be the friction. Now, first of all, if you guys think about it, I need to talk about the vertical forces acting on this object. I need to think about the vertical forces acting on an object. And if I take this as a plane, as these two vectors as the reference, this is going to be the normal reaction. I can represent it with R. And if I'm talking about the sum of the vertical forces, there must have been a downward component of this weight over here. And this component over here, this is going to be the vertical component of weight. This is going to be the horizontal component of weight. The thing is that which component would be effective over here? Would it be Wy or would it be Wx? Ji Hassan.
Wait, sorry, could you repeat that question, please?
Well, are you guys not even listening me?
Repeat it, please.
Well, I'm just asking you that if you've got R and if you've got Wy over here and Wx, which component is going to be effective whenever you're talking about the summation of the vertical forces?
The X.
Wx. So do you really think that I'm going to keep the normal reaction equivalent to Wx?
Oh, no. Why?
Exactly. It has to be Y. Got that? And there must be some sort of an angle. For example, this angle is 30 degrees. So remember that this angle is going to be 30 degrees as well. So I can just simply do R equals to Wy cos 30. Got that? Okay. So that is going to be the reason that how can we resolve the forces. Got it? If you've got Fx and Fy, things gets quite easy. You just got F cos theta and F sine theta. But the resolution demands even more concern over here like this. For example, you've just got a bar over here, and that bar is hinged with this rod with the help of a string, which is acting over here like a 50-degree thingy. And there must be some sort of a weight of this rod as well. A weight must be acting downwards, right? Over here. Now, which component of tension you guys going to take as effective? First of all, let's resolve this thingy. How can you resolve it, Jasmeet? You've got the tension acting over here. How can you resolve the tension? Yeah.
I'm not sure.
Jasmeet,
Can you explain it again, please?
Well, for example, if you've got this rod, right? I've just hinged this rod at this point, and I've just attached a string, with this rod as well. We've got a point over here. This is the string, right? And I'm just talking about the vertical forces. So I've got the downward weight of this rod, and I've got the tension over here as well, right? Which component of tension will be taking as effective? Or how would you resolve the tension? For example, let me talk about it in detail. For example, you've got tension over here, right? And the vector of the tension, the resultant vector of the tension is somehow like this, right? If I need to resolve this tension into components, this is going to be the x component of the tension, right? And this is going to be the vertical component of the tension. We've got an angle over here, and that is 50 degrees. Got that? Now, which component of the, this is T. I'm pretty sure you guys get to know that this is going to be T cos theta, and this is going to be T sine theta. Got that? And there is a downward force acting over here, and that is equal to the weight. Now, if you need to do any sort of calculations, right? For example, they've given you that the weight of this rod is something like 25 newtons, and you need to calculate the tension in this string. So would you be keeping W is equals to T cos theta, or W is equals to T sine theta if the rod is in total equilibrium?
Would you use sine theta?
Exactly. Because sine theta is an effective component for the weight. So we're just going to use W is equals to T sine theta, and we'll get the tension from here. Got that? So that is how we talk about the resolution of forces. We need to resolve the forces or whatever vectors we're talking about in a concerned direction. If you're talking about the weight, you need to take the horizontal component of the normal reaction force, right? If you're talking about the normal reaction force and you need to split the weight down, you need to split weight into Wy and Wx. Got that?
I just have a question.
Yeah.
Is the resultant force the same as the normal force?
The resultant force is the same as the?
Normal.
In this case or in this case?
First one.
In the first one. Well, the normal reaction force is same as the, can you say that again?
Resultant.
Well, resultant force must be downwards over here, right? I've been telling you guys that this object is moving downwards. Got that?
Yeah.
Okay. So this R must be equal to the Wx because the object is not moving down. The object is not moving, not moving up as well. The object is just sliding down. So it must be equivalent to the, somehow like this. You need to equate this one with this one. Got that?
Okay. Thank you.
So that is how we talk about the resolution of the forces, right? Now, the next thing, after the resolution of the forces, we just need to have some sort of knowledge about the Newton's laws of motion. The Newton's laws of motion. So nobody is going to tell you about the first statement, second statement, third statement, right? The questions from the first, the questions from the first law are very generic. If you talk about the second law, the statement of the second law is that the resultant forces acting on an object should be equal to the product of mass and acceleration. Got it? Now, if you want to apply the second law on this object, I'm going to get back to this object. If you're going to apply second law onto this object, how would you do that? G, Emmett. You guys can open your mic. Are you guys scared or shy? It is feeling like a graveyard over here.
Mm,
Mm-hmm.
Newton's second law of
For
motion
the second law, can you just say the resultant force is equal to the rate of change of momentum? We can say that, I mean, but the thing is we, sometimes we need to apply the second law as well. For now, I'm just talking about how you're going to apply second law of Newton. For example, if somebody is just asking you to calculate the acceleration of this object downwards, how would you do that?
You'd get the resultant force.
Exactly, get the resultant force. How would you get the resultant force now?
By taking away all the three forces together.
Are we talking about all the three forces now? What are those three forces you're talking about, Hassan?
The normal contact, friction, and the weight, no?
Well, first of all, any one of you, can you guys tell me that is there any motion of this ball along the vertical direction? Is the ball moving up or moving right down through this point?
No.
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 The body is not moving either up or down. The only forces we should be concerned about is this one, the driving force, is the frictional force, and the x component of the weight. Got that? So we've got
Yes.
three somehow the horizontal forces, and that's going to get us the resultant force. We're just going to equate it to the product of mass and acceleration, and we might get the acceleration from there. Now, since the body is moving down, so all the forces directed in this direction should be positive, and this one is supposed to be negative, right? Now, this force
sir.
is going to be, the driving force. It might be given, for example, the downward force acting on this object is somehow like 5 Newton, right? You've got that. 5 plus this component of the weight, and that is going to be W or mg. This was the opposite mg sine theta. And then we've got the frictional force. How do we calculate the frictional force? Take away mu r and equate it with ma. Got that? So this is how you apply the second law of Newton whenever there is a resultant force acting on an object. Jasmeet, did you get to know that?
Where does the 5 come from?
Well, 5 is just, I'm supposing, this is going to be the driving force over here. Right?
Okay.
Everybody going to let you know about the coefficient of friction if there is any. You've got R, you've got M, you've got G, you've got theta, you've got mass as well, and you'll easily be able to calculate the acceleration. Got that?
Yes, sir.
Okay. So
Yes.
this is how we apply the
What's the
second law.
U?
Well, mu
in
is
the
the
equation?
coefficient of friction. It is given as well, right?
Oh,
Remember
okay.
that the friction's formula, you guys have done that, and that is equal to the product of coefficient of friction times the reaction force, this reaction force. If nobody gets to understand this example, I can explain it again.
Can you
What do you mean by the
Jasmeet,
coefficient of friction?
Gigi, Hassan?
What do you mean by the coefficient of friction?
Well, coefficient of friction is a measure of friction, and it is a medium specific. Wood can have its own coefficient, iron can have its own coefficient, so it is just a constant, right?
Thank you.
And R is a normal reaction force. Anybody wants me to explain it again?
Yes, please.
Okay, for example, let we talk, we are talking about a simple sort of a slope like this thingy, right? And
Yes.
we've got an object over here. There are some multiple forces acting on this object. There must be an upward force. That is going to be the normal reaction. There is going to be a downward force, which is going to be the weight, right? There is going to be a oppositional force, and that is going to be the friction. This is going to be the driving force. This is going to be FD. Got it?
Yes.
Now, if I'm taking this plane, I'm taking this plane as a reference. This plane, this plane, this plane. And everybody among us know that the ball is not moving up, neither the ball going to move down, right? So all the forces acting in this direction should be equal to each other. So normal reaction should be equal to this one. So the only appreciable forces are going to be this one, this red one, this FD1, and this F1. And by just talking about the resultant, we can calculate the resultant. How can we calculate the resultant? By just doing, this is the driving force. This is going to be FD, right? Plus the horizontal component of the weight, and that is going to be sine theta, minus the frictional force acting on an object, and that is going to be something like minus the friction. Friction can be given to you, or even in some questions, the examiner tells us that there is a negligible friction. So friction automatically becomes 0. And we can equate it to MA, right? So everybody knows about the Newton's second law. But applying this equation on examples or the questions in the exam often gets a bit messy, right? So you need to know that how can we apply all these forces and equate it to M and A. So at the end of the day, if you've got all of these things, you'll be able to calculate the acceleration. I'm supposing that every other thing is given, right? Okay. Now,
Wait, is there an instance where one of them isn't given, and then you'd still have to find the
well,
acceleration?
even if there is no given, we can't really work it out. All of these things must be given. For example, if you've got the mass, it is understood that you've got the W, you've got the FR, and driving force must be given as well. So all of these things are often given, right? The questions without any one of these things would make sense. Did you guys get that?
If friction is different for each material, how would you work out the friction?
Well, friction, the formula for the friction is mu r. and R is equal to mg, right? The coefficient of friction is given. M is the mass of an object. G is the gravitational acceleration. Got that? But in many cases, examiner tells us that there is a negligible friction. Okay.
Wait, what does
Okay.
R represent again?
R is the normal reaction force, this one.
Oh, okay.
Okay.
And
this
the U
must
is
be equal
always
to-
given, right?
U is always given. It is a constant related to the medium.
Yeah.
Yep.
G. Should we proceed from here now?
Sure.
That's
Okay.
fine with me.
Now the
Yeah.
third law. If we talk about the third law, everybody gets to know what the third law is. But the important point is that what are the conditions for the two forces to be the third law pairs, right? Okay. So what are those conditions, Ariba? What are the conditions for two forces to be Newton's third law pair?
I'm sorry, pairs?
Yeah, Newton third law pair.
Don't they have to be similar in size?
Well, that they need to be.
Isn't it?
Isn't
There
it
is
like
the
if they
exact.
have to have like the same exact type of force? It's like
Well,
equal
exactly.
magnitude, opposite direction, like that.
Apart from these two things, do you have any other conditions for forces, for two forces to be Newton's third law pair? Very important question.
Like if it's a contact force, the reaction force should be contact force. If it's gravitational, then reaction should be gravitational, like that.
Exactly. Somehow
The-
like that, right? So whenever you're talking about the two
the
forces to be Newton's
exertion of
third
an
law
equal
pair,
opposing
first of
reaction.
all, exactly. First of all, they must act on different objects, right? They must act on different objects. Second, there must be same type of forces. Got that? If you're talking about the contact force, the other one should have been a contact force as well. Got that?
Yep.
So these two are the notable conditions which everybody needs to know, that they must act on different objects and they must be same type of forces. Got that? So we've got a question now. They should be exactly, Bilal. They should be in the opposite direction, right? And these two things are well known. They should have same magnitude as well, right?
Action and reaction, right?
Exactly. But these two notable ones, right? Not everybody knows them. They should be acting on the different objects. They should be same type of forces. Okay, so we've got some talk about the Newton's laws of motion. And after the Newton's laws of motion, now we have got some sort of thingies about the moments, right? We need to talk about the moments. Gee, a simple definition of moment, Emmy. Is the force times the perpendicular distance from the pivot. Okay. So that's a simple thing, whenever you talk about the moment, it is the force times
Depending if
perpendicular
it's-
distance. But remember that this distance needs to be perpendicular. Got that? Okay. So the important thing about the moment is the principle of moments, right? And we'll talk about the principle of moments right after 2 minutes. Okay. Just mind being back.
What, do we have a break?
I believe so.
Well, how long?
I don't know. He's gone on mute.
All right. Jasmine, you all right?
Yeah.
आप लोग इतना डर रहे क्यों हो? He's very friendly. Turn your mics on.
I have a
Fine.
loud house.
Yeah, I can hear your mum in the back.
Oh, right. me too.
Exactly.
I understand your pain. Don't worry.
Harry, is your computer all right? Harry?
Everyone else seems to have curled up into a ball. They're very scared of him. Oh, Harry?
Harry?
Wait, where's Harry?
Wait, is he not on the...
No, he's disappeared.
Thought he'd be
No, his computer couldn't handle it, he said.
Where did Harry go?
Let me call.
This is a doom scroll break.
Indeed. Do you understand what he's been teaching so far?
Yeah,
I'm gonna
simple.
ask Washma to re-explain, man.
Wait, I saw a Workshop was meant to be here.
She
She's not
said
here,
she
buddy.
would.
Yeah, well, like, A,
No, I
B.
asked her. She said she's not joining today.
Well, is there one
Someone
tomorrow?
re-explain the formula.
Yep, no Vashma. What did you say, Jasmine?
Oh, she isn't.
Re-explain the formula.
Which formula? This one?
No, not that one. I know the moments formula.
You can write on the
Which
screen,
one?
bro.
Talking about the mechanics one?
You can write on the screen.
Okay, guys.
Yeah.
Now we've got the
Oh.
principle of moments, right? Okay, so we've got Muhammad Yasa. Ji, Muhammad Yasa. What do you think about the principle of moments? Any particular statement about that? Yes,
Clockwise is equal to sum of clockwise.
exactly. The clockwise moments should be equal to the anti-clockwise moments. So we have got the clockwise moments that should be equal to the anti-clockwise moments. Very important question across Cambridge and Edexcel, and almost, in every paper. Now, for example, if I talk about an example I've given earlier on about this rod, where is that rod? Okay, over here, right? So you can see that this is a rod in equilibrium, right? For example, I'm keeping some sort of a weight over here as well. I've got the weight of the rod over here, then I've got the tension, and then I've got a force acting over here as well, right? So first of all, what we need to know, they're asking us to calculate that the weight over here if the rod is in equilibrium. So first of all, we need the pivot, right? So which point, remember that if the pivot is not given, you can assume any point to be the pivot if this rod is in equilibrium. And in this instance, I'll be keeping this point A to be the pivot. Got that? I've got this distance. I've got the total length of the rod as well. And I've got, every required length as well. For example, let it be 10 meters. So I've got this distance, I've got this one, I've got this 10 meters as well. Remember that whenever you guys are trying to attempt the principle of moments, first of all, you need to understand that how many forces are acting on that rod. In this case, we've got the tension over here, we've got the weight over here, and we've got the weight of the rod over here as well. So we've got three forces, and one of them should be the contact force. But since I'm taking this point to the pivot, the contact force can not be considered, or it can be neglected. Okay. How would you guys calculate the moment of this due to this tension? And would that be clockwise or anti-clockwise? Ariba?
I'm actually kind of confused. I don't know what we're getting the moment for.
Well, for example, this is just an example.
Wait, could
We've
you
got
redraw it
Right.
on a clearer slide, please?
Okay, sure.
Yeah.
Are you guys not loving my drawings?
Not
Okay, so
particularly.
we've
No,
got
it's
a
not.
rod over here. Okay. This is the rod over here. And we've attached some sort of a beam with this rod, right? And this beam is also being supported with the help of a string, right? And for example, over here, we've got Asad standing,
Why me?
right? We've got the total length of the beam. We've got this point to be the A. We've got this point where the tension is acting right in the middle of the rod. And at the same point, we must be having some sort of a weight as well. We've got this object as well, right? Now, first of all, if you're talking about the moments across A, how many moments you think, will be able to generate on this rod? Ariba?
Okay, so there would be the weight of the rod itself and the weight of the
Exactly.
person.
Weight of the person downwards as well. And any
The
other moment?
tension of the rope.
the moment due to the tension as well. So we've got 3 moments in total. We might be having this moment as well, but I'm taking point A to be the pivot, right? The angle over
Right.
here is 50 degrees. Got that? Now, how would
Got
you
that.
set up an equation for the principle of moment? The moment due to tension would be clockwise or anti-clockwise?
Anti-clockwise.
It is going to be anti-clockwise. The
How do you
moment due
tell?
to the, well, because this object needs to rotate around the pivot. So it
Because it's
must be
pulling it
rotating
up.
like this,
Oh,
right?
okay. I got it.
It is pulling it up. This object needs to
Oh,
rotate
okay.
around the axis as well.
That
So
makes
this needs
sense.
to be clockwise. This is going to
that's
be
okay.
clockwise. This is going
Yeah.
to be anti-clockwise. We've got a question. Okay. Emmy, who isn't at home? Why you're asking me this thing? Darling,
No,
Oh, no,
no,
don't worry
that's an
about it.
old thing. That
you
was
don't
during the
speak.
break. That was during the
Watch my
break.
Okay.
didn't end.
And then we've got the weight of this person as well, right? And that must be somehow like this. Got it? So we've got 2 clockwise moments and we've got 1 of these anti-clockwise moments. Got it? So when you're going to talk about them, the anti-clockwise moments should be equal to the clockwise moments. Now, Yasa, what is going to be the anti-clockwise moment due to the torque if the tension is not given? And this distance is, let it be 5 meters. What is that moment going to be? Yasa, what is going to be the moment due to this rod?
T times T sine theta times
T sine
5,
theta times 5. Why are you taking T sine theta, not T cos theta?
because perpendicular.
Perfect. So I'm going to keep it equal to the weight of the rod times the center. That is going to be 5 as well. Plus the weight of Anas times the total length, the perpendicular distance between them. And that comes out to be 10. Got that? Ji? So we're just going to simplify it down. If you've got this weight, we'll easily be calculate the tension. Right? Did you guys get that? So that is how we talk about the principle of moments. But before we get to the other topic, I want us to try out some examples about the principle of moments. And we'll be talking about...
Where did you get 10 from?
Well, 10 is the total length.
Oh, so 5 is midpoint. Okay.
Exactly.
Got it.
Okay, so... Okay, we've got some questions over here. We'll do some of the above questions, but before that, we've got this right on your screen. We've got a bicycle pedal is connected to a circular chain ring by a lever, right? A person of weight W stands in the pedal. The lever is at an angle theta. You know, this is an angle theta over here to the horizontal as shown in the diagram below. We've got this. Determine the moment of W about the pivot when theta is equal to 24. We've got the length of the lever. We've got the weight W to be 580 newtons. Gee, so how would you guys get the moment of W about the pivot when theta is equal to 24? Gee, Jasmeet. Hurry up, hurry up. We need to cover a lot of things.
Should we use cos or would we still have to use sine?
Well, it's up to you. Think about it. What we'll be using? Would it be cos or sine?
It'll be cos because it's against the horizontal.
It is again
The angle is to the horizontal. It's not to the
Exactly.
perpendicular.
So we're just going to set up that equation, and that's going to be 580 cos 24 times 0.21. That is going to be the moment of W about the pivot. We've got that. Now, this is an important theoretical question. The chain ring exerts a force of F on the chain, right? And F is proportional to the moment about W. Explain how F changes as theta increases from 0 to 90 degrees. You do not need to do any calculations. So if you're increasing theta from 0 to 90, how would the force exerted on the chain ring would change? Emmy? Okay. G, Hassan, what can you say about it? As theta changes from 0 to 90, how would the force change?
Would it increase?
Would it?
Increase?
I
Well,
thought
how?
F
You need to.
decreases.
The
F
force is
decreases.
proportional to sine
Oh
of theta.
yeah, the FD does decrease. Yeah, F does decrease.
How? G, are you
Because
explain?
it's like-
Can you explain that?
Okay, I guess. I just like thought that F is gonna decrease as theta is increasing and it would become
Okay.
0 at 90 because like F is inverse to cos theta.
Exactly. Brilliant. So you've got the,
Thank you.
the moment, and that moment has to be F times L cos theta. Jasmeet just told us that, we've got cos theta over here. Now you talk about this cos theta from 0 to 90. The cos theta gonna decrease from 1 to 0, right?
Cos of 90 is 0.
You get that? So the torque would eventually decrease. And as the torque is decreasing, we're bound to say that the force decreases as the theta gonna increase. Got that? Okay, so we just need to remember the mechanics of a formula whenever we're talking about such question. We've got another one over here. We've got some sort of a bus, right? A film involves a gang of bank robbers making a gateway on a bus loaded with the gold bars. The bus spins out of control and ends up balancing on the edge of a cliff. The bus is balanced on a pivot that is at a distance y from the center of the bus. The center of the mass of the gold is 1.5 meter from one end of the bus, and the center of the mass of the bank robbers is 1 meter from one end as well, right? We've been given, well, everybody knows that what do we mean by the moment of forces? The length of the bus is 11 meters. So I'm just gonna label it over here. The length of the bus is somehow 11 meters. And apart from that, the weight of the gold bars is 31,000 newtons. 31,000 newtons. And the weight of the robbers is going to be 8,700 newtons. And we are supposed to be calculating the distance y when the bus is balanced on the cliff, right? So we are supposed to talk about this distance y. G just means how would we set up the equation for the for the moments?
For the distance, can you just put 15.5 add y and turn it into like an algebra equation?
15.5.
The 1.5
Okay.
add y multiplied the force, and that would equals the what do you call it? The moment on the other side. And you can turn it into an algebraic equation.
Are you talking about the principle of moment, or you've got any other equation in mind?
Oh, but I thought you were asking about B. Oh.
Yeah, I'm asking about B. We just need to calculate y from here. So how are we going to do that? First of all, identify the moments we've got, right? So if we're going to talk about the moments, if we're going to talk about these moments, we've got the pivot over here. I'm going to take this point to be the pivot, right? Now I've got how many forces I've got? I've got 31,000 for the gold. We've got 8,700 for these people. I've got the weight of the bus as well. So I've got 3 moments in total. This one is going to be clockwise or anti-clockwise? Moment due to the gold bars.
Anti-clockwise.
And these 2 moments, the moment due to the weight of the bus and the moment due to these people is going to be clockwise. So the moment of 31,000 newtons across this pivot should be equal to the sum of the moments due to the weight and these people. So how I'm going to apply that equation? I've got 31,000 times what is going to be the perpendicular distance between the gold bars and this point? The total length of the bus is 11.
Can you repeat that?
Well, the total length of the bus is 11 meters. So we get to know that the distance from, the total distance up till here is going to be 5.5, right? I'm just asking you guys for this distance. What is this distance going to be?
It's going to be 5.5 minus y.
And well, this distance, this one is 1.5 as well. And we're talking about the moments at this point.
Yeah, so So you take that away from that as well.
So 5.5 take away 1.5, take away y. Got that?
Yeah.
So that's going to be 4 minus y. Everybody got to know that how I calculated the moment.
Yes.
Okay. And that should be equal to the moment due to the weight of the bus, right? What was the weight of the bus now? Was it given? It should have been
Yeah, 31.
32,000 newtons, right? So I've got 32,000 newtons over here, and the distance from the pivot from the to the weight is going to be y as well. Got that? And I'm just gonna add it into 8,700 times. What is going to be this distance now, Ariba?
That's just 5.5 minus 1, so 4.5
So this is going to be 4.5. We're talking about the distance
plus
up till this
y.
point. So plus y. So that is going to be 4.5 plus y. Got that?
Yeah.
Okay. So we've got 4.5 plus y. Sorry. Yeah, plus y. Now I've got this algebraic equation, right? And I'm pretty sure you guys can calculate the y from here, which is going to be the distance of this pivot from the center. Is that clear?
Yeah.
Right. So that is how we deal with the problems involving the moments. Well, we were talking about an example like this, right? Conditions for the object to be in equilibrium, we all already know that. By taking the moments about A, determine the tension in the wire. So we just need to take the moments about A and determine the tension in the wire. How are we going to do that? Can any one of you explain? Hassan. You've got the whole questions before you as well. Gee, Bilal, what do you think about it? How can we calculate the tension in this string, this one?
We're going to use cos 50 now.
We'll use,
Cos 50. And then times it by the distance.
well, for example, if I can just elongate this wall over here. Now, first of all, I'm going to take the moments about A, right? So there must be some sort of a moment due to this mass over here, right? There must be some sort of a moment due to the weight of the rod, and there is some sort of a moment due to the tension in the rod as well, right? This one is going to be anti-clockwise. These two are going to be clockwise. If you guys remember, we just talked about an example like this. Now, what we're going to do, we've got this angle 50 over here. The moment due to the tension is going to be, T. I need which component of tension from here? The perpendicular component, right? And this is going to be sine 50. So T sine 50, the distance of this point from the A is going to be the half of 0.65, whatever it is, right? And I'm going to equate it to the mass of to the weight of the rod. What is the weight of the rod now? 33 newtons, right? So 33 times 0.65 divided by 2 as well. And I'm just going to add it into the mass due to this sort of a thingy. What is going to be the mass due to this thingy? The length of the shelf. And do we have the mass of this object? 0.12. A cup of weight 1.5 newtons, right? So we've got 1.5. And what is going to be the perpendicular distance between this cup and the A? That is going to be, the total length is 0.65, just take away 0.12 from here, right? So 1.5 times 0.65 negative 0.12, and I'll get myself the final answer. Got that? So by just solving this equation, I can easily calculate tension from here. Is that clear, everyone?
Yeah.
Okay. So that is how we're going to talk about this example. I'll leave this question for you guys, right? A ladder and a hinged bolt sort of a thingy. And now we'll get back to the next topic. And what was that after the principle of moment, what we're going to talk about? We've got the moments. We've got the laws of motion.
Projectile motion.
We've got the resolution. We've got the projectile motion now, right?
Yeah.
Now, projectile motion is very important as well, right? So whenever we are talking about the projectile motion, gee, Ahmed, can you explain what is a projectile motion in very simple words? Mhm. Ji, Amit, what is a projectile motion?
Yes, sir. Projectile motion was the type of motion where an object was launched into the air and was launched into the air in a curved shaped path where it acted on its own
In
momentum
very
and
simple
gravity.
words, we can just simply say that it is a two-dimensional motion, right?
Two-dimensional.
And whenever we talk about two-dimensional motion, we've got, for example, I'm just talking about 2D parabolic motion. Exactly. We've got some sort of a motion where a ball moves like this, right? Now, the basic thing that you guys need to understand that whenever you're talking about the two-dimensional motion, it got some sort of X, motion along the horizontal as well. And at the same time, it got some sort of a motion along the vertical as well. And we need to understand all the aspects of the horizontal motion. Remember that whenever you're talking about the projectile motion, you guys are basically neglecting air resistance, right? There is no air resistance acting on this object. So we've got the horizontal motion, we've got the vertical motion as well. And now we just need to talk about that. Now, is there
They're
any
independent,
force?
right?
Yeah, they're independent,
They're
exactly.
Yeah.
Now, first of all, is there any force acting along the horizontal direction?
The driving force.
Well, the projectile moves freely. It do not have any driver.
No, if it's thrown, no.
If it is thrown, that is an initial pull only. So
Yeah.
whenever you guys are talking about the horizontal force, remember that there is no net force acting along the horizontal, right? What does that mean? That the acceleration of that object is going to be 0. And whatever the velocity, initial velocity along the x-axis was, that is going to be the final velocity along the x-axis as well. So there is no change along the horizontal in the velocity. Got that? Now, this is the basic concept which many students fail to understand. That the initial velocity, if you're talking about the horizontal, the final velocity, if you're talking about the horizontal, they're bound to be the same. But when you talk about the vertical motion is happening under constant influence due to gravity, right? So net force in this case is not equal to 0. What does that mean? The acceleration would also be non-zero. And what does that mean now? That whatever initial velocity we have got, it would be different from the final velocity. Got that?
Yes.
Right? For a projectile motion, the velocity at the highest instant of time is going to be 0. Okay? So, these are the few things which students needs to understand, that horizontal and the vertical motion in the case of a projectile motion are totally independent of each other. For example, if somebody is talking about to calculate this distance, it is totally a horizontal distance, right? And you guys are just given with that the ball was launched at a velocity of 23 meters per second with an angle of 30 degrees with the horizontal. Got it? If you guys need to calculate this distance because the object is not accelerating, so the distance would straight away be 23 cos 30 times the total time the body going to take to reach at this point. The time might be given, right? So it is just the velocity, the vertical component of velocity times the time. That is how you talk about the distance along the vertical. But whenever you're talking about the distance along the horizontal, it has to be, since the body is accelerating, so you need to take acceleration under consideration, and that is going to be half gt square, right? So that is how you calculate the distance along the x-axis, and that is how you guys calculate the distance along the y-axis. So this is going to be vx times t, and this is going to be half gt square. Did you guys get that?
Yes.
Yeah.
Now another sort of a thingy over here. We've got we've got the horizontal distance, we've got the vertical distance, but how would you calculate the components of the velocity. This 23 meters per second is the resultant velocity, right? This 30 degrees
Yeah.
is the launch of angle, is the angle at which the ball was launched, right? So if you want to calculate the initial vertical velocity, that is going to be the velocity, the resultant velocity times the sine 30, because you're talking about this component of the velocity, right? If you're talking about Vx, that is supposed to be V cos 30 as well over here. Got that? So I've got V sine 30, I've got V cos 30 over here. And if you want to get the resultant velocity, that would again be Vx square plus Vy square. And the angle, the direction of the projectile would be V, the opposite, this one, over the adjacent Vx. Got it? So these are some of the properties about the projectile. But since the topic might seem a very simple one, but the questions related to the projectile motion, you guys often mess up. So for example, if we talk about this sort of a question, for example, right over here, you have launched a ball on a horizontal ground is kicked towards a vertical wall. The ball has an initial velocity u at an angle 38 degrees to the ground, right? The ball travels a horizontal distance 9 meters before striking the wall at a height above the ground. The horizontal component of initial velocity is 9.5 meters per second, right? So you've got the horizontal component of velocity straight away, okay? And the air resistance is negligible. Show that the time taken for the ball to reach the wall is 0.95 second. Ariba, how would you do this question? How would you get me the time for the ball to reach the wall?
Sorry, I'm just rereading the question again.
Hurry up,
Okay, yeah,
hurry
so
up,
just
hurry
take the
up.
distance over the horizontal speed. Do
Exactly.
9 over 9.5.
Exactly.
And
So we
give
just got the
0.95.
time, and time is going to be the distance, which is going to be 9 divided by the horizontal component of velocity, right? And that is going to be just 9.5. Got it? Now, in the similar way, we've got the vertical component of velocity. Bilal, how would you calculate the vertical component of velocity if you've got things like that? You've got the Vx, that is 9.5. You've got the theta, and that is 38 degrees. How would you get me the resultant velocity? Are they asking you for the resultant or the vertical component? Yeah, vertical component of the velocity. How would you get me Vy if you've got Vx and theta and Vy? Sorry, not Vy, Bilal. Okay, so what he's talking about? Sine theta. Okay, for example, if I'm using sine theta over here, I do not have the resultant velocity straight away. I would not have the vertical velocity straight away from here. Because if I'm going to use sine theta, that would be the opposite, which is going to be Vy upon the resultant, which is going to be the this velocity. I do not have the resultant velocity yet. I just got the 9.5, which is the horizontal velocity. So I can use just tangent theta over here, right? Tangent theta is going to be the opposite, which is Vy upon Vx. So by just doing Vy is equals to Vx times tangent theta, I can calculate the final answer. Got that, Ji? Right?
Yeah.
So we just do
Wait,
not.
sir, I thought we would do something like 9.5 tan 38.
9.5 times?
That's the horizontal one.
9.5 tan 38.
9.5 times tan 38. Well, that is what I've done. Vx is
Oh, okay.
9.5 and tan
My bad.
38. This is going to be something like this. Okay. Now, the
Okay,
last thing
thank
is
you.
that we need to determine the height at which the ball strikes the wall. Jasmeet, the height at which the ball gonna strike the ball. Yeah. Mm-hmm.
Wouldn't use the CVAC version.
Do we even have Jasmeet with us?
We should
Wait,
do.
wait, wait.
I'm right here.
Okay, Jasmeet, why you're not
Sorry,
answering?
but I
Why
had to
you're
go
not
do something. I have messaged Asad.
you're messaging us as if Asad is teaching you, huh?
Yeah.
No, I asked him to
Back
tell you
off.
I had to go do something.
Okay,
Oh.
have you read the question now?
Sorry, I didn't see your message.
Can you re-explain that, please?
Well, you've got this question, right? Okay, well, you've got this question, right? You're launching a ball from here, right? And it's striking a wall at this point. Okay. I've got the time, I've got the vertical component of velocity, I've got the horizontal component of velocity, and I'm just asking you for the height. Gee, Bilal, any guesses? How would you get this height?
I've got a guess.
Okay, as Hassan बताएं.
Wouldn't you use v squared equals u squared plus 2as?
For example, if I'm going to use v square equals to u square plus 2as, right?
G.
You've got the initial component of the vertical velocity. That is, understood. You've
Yeah.
got a as well. But how would you get me the final velocity when the ball is moving in a vertical direction? We never know that. We do not have the final velocity. Got it?
You need
How many marks is the question?
Well, it must be a 2 marker, I guess.
Okay.
G. Remember that if you want to calculate this height, this distance by the projectile was covered in 0.95 seconds. Remember over here, 0.95 seconds. So I just need to calculate how much it is vertically at a height of 0.95 seconds. So what was the initial component of the velocity? I'm just going to use, h is equals to ut plus half at square. Got it? So s is equals to ut. What is going to be the initial component of the velocity now? Did somebody calculate Vy from here? 9.5 times tangent 38.
7.42.
7.42. So you've got 7.42 from here, right? The time the projectile going to take to strike that ball is going to be 0.42, I guess. No, 0.95. Got that? Initially, the ball was moving up, so I'm going to take the acceleration due to the gravity to be negative. So I've got half times 9.81 times 0.95 square. Got that? So by just calculating all these things, I'll be able to calculate the distance. And what is that distance coming out to be now?
2.62 meters.
2.62 meters. So that is how we're going to calculate the distance of this ball from the surface right now, right? If anybody among you guys didn't get that, I can explain it again. Everybody
Makes
got
sense.
that? Okay.
Yeah, I got that.
Okay, now we've got another example. Okay, we've got the tennis players can practice using a tennis ball machine. The machine projects tennis balls horizontally at a height of 2.54 meters, right? Show that the time taken for a ball to reach the ground is approximately 0.7 seconds. How are we going to do it, Jason? How you'll get me the time taken for a ball to reach the ground? Yeah. Do we have Jason with us?
Yeah,
We
sorry.
Okay, Jason, I'm just asking you, how would you get me the time taken for a ball to reach the ground?
Could you use wait, yeah, I don't know. Sorry.
Well, for example, first of all, the object is projecting downwards, right? From a height of 2.54, and we're supposed to be calculating the time. So this is some sort of a, I'm just going to talk about the vertical motion down there. I've got S equals to ut plus half gt square. The initial velocity at the highest point in the vertical motion is supposed to be 0. So I've got S equals to 0 times t. The gravity downwards should have been 9.81. And I'm supposed to calculate the time. The distance the projectile going to cover is 2.54. So I've got 2.54 equals to half times 9.81 times t square. And that t square comes out to be 2 times 2.54 divided by 9.81. Can anybody do that? Get me the time from
0.7.
here. It is not 0.7, right?
Yes.
So I've got 0.7 from here. The ball lands on the ground at a horizontal distance of 17.89 meters from the machine. Calculate the velocity of the ball as it is projected from the machine. So ball is going to cover a total distance of 17.89, right? And we are supposed to be calculating the velocity of the ball as it is projected from the machine. Velocity of the ball as it was projected from the machine. Jasmeet, how would you get me the initial velocity of the ball?
You can do
Yeah.
speed equals distance over time.
Speed
And
equals to
then,
distance over time. Okay, we're going to calculate the speed, right? Okay.
yeah,
Which distance you're going to take now?
the 17.89.
And what do we have for the time?
The 0.7.
0.7.
7.
Achha. Bilal, why can't we take 2.54 as the distance?
That's vertical
Why can't
motion.
why can't we take 2.54 as a distance? Yeah.
Because that's the vertical distance.
Because the velocity, you know, we are concerned about the horizontal component of the velocity, right?
Yeah.
And if you're talking about the horizontal component of the velocity, that would get you something, okay? Because the vertical velocity at that point has to be 0. Is that clear? Okay. Now we've got the C part. The initial velocity of the ball is increased. Explain how increasing the initial velocity would affect the angle at which the ball hits the ground. If you are increasing the initial velocity, how would it affect the angle at which it's going to strike the ground? Hassan?
Would it decrease?
Angle would?
Decrease.
Well, you need to give me a reason for that.
Is it because the horizontal component will get bigger?
Horizontal component would get?
Larger, meaning that it would go
Well,
through
for
a
example,
bigger
if we talk
distance.
about this sort of a thingy over here, well, you guys know that tangent theta from here comes out to be the velocity along the vertical upon the velocity along the horizontal, right? So if you're projecting it at a higher speed, the Vx is bound to increase, right? Because Vy would still be the same, right? Vx is going to increase. If Vx is going to increase, tangent theta as a whole is going to decrease because tangent theta over here is inversely proportional to Vx. And as you decrease tangent theta, would theta decrease or increase? Theta would decrease as well, right? Got that? So that is
Yeah.
how we need to answer this sort of a question. Okay. By the way, sir, where can we find the recording of this class? Well, I'll upload it on the YouTube.
Wait, so was that right?
Exactly. That was right,
Yeah,
but that
thank
was
you.
just a fluke, Hassan.
How was it? Yeah, sure.
Okay.
How
So
about
we've got
Hassan?
this sort of a projectile motion now. Okay. If you guys got any sort of questions from the projectile motion, you can ask. Otherwise, we'll get to the conservation of energy now.
Good to go.
Anyone? Okay. So we've
Yeah, I'm
got
good.
the is there any question? So we've got the next question, next topic now, and that is all about the energy. So when do we talk about the energy? You know, first of all, everybody knows that we have got the kinetic energy, energy processed by a body due to its motion, right? Secondly, we've got the potential energy as well, right?
Yeah.
And then potential energy got some different types. One of them is the gravitational potential energy, and then we have got the elastic potential energy. But these things don't hurt students, right? The thing that helps us to get some score is the law of conservation of energy. You need to understand that how can you mathematically set up the law of conservation of energy. For example, let me take an example over here. You've got a slope over here, and the ball is moving down from this point to this point, right? There is some sort of a friction as well. How would you set up the equation for the ball moving downwards? First of all, is some sort of, is gravitational potential energy increasing or decreasing as the ball is moving down? Decreasing, right? So what the
Decreasing.
equation would tell us, that the increase in kinetic energy, right, is equal to the decrease in the potential energy, take away the work done by the frictional forces, right? Sometimes, the examiner tells us that the friction is neglected, so you don't need to include this sort of a thing. Sometimes we need to do that, right? So the increase in kinetic energy would be settled up by somehow like this: half mv square minus half mu square equals to mg, the upper height, that was h1, minus mg h2, minus the work done by the frictional force. Friction times the distance. Got that? So you've got half mv square minus half mu square plus mgh1 minus mgh2 minus f times d. Now this is the equation that you guys need to understand. In some cases, there is the changes are not taking place along the kinetic energy or the potential energy. In some cases, the changes are taking place along the the kinetic energy and the elastic potential energy as well. For example, you've got a ball that is attached to some sort of a spring over here, right? Whenever you're going to pull this ball downwards, it would lead to some sort of an increase in elastic potential energy, right? And when you're going to lose that ball, the ball going to fly up, and that would again increase the kinetic energy in this case, right? So we've got the increase in the kinetic energy, and then we've got some sort of an increase in the elastic potential energy. So sometimes we are talking about the potential energy, but sometimes we are talking about the elastic potential energy, right? How do we calculate the elastic potential energy though?
1 by 2 kx squared.
1 by 2 kx squared, that is about the extension, right? So we've got these things covered. In the law of conservation of energy questions, you just need to understand that how you're going to apply this equation. Got that? Now, after that thingy, we've got something related to the power, how the power is transmitted in a system. And whenever you're talking about the power is the rate of change of work done, yani work done upon the time. But there could be some other formula for the power as well. Well, if you guys remember the work done is going to be force times the displacement, got that? Upon the time. We've got force times the displacement upon the time. And we can rewrite this equation to be F times D upon T, and that comes out to be F times V. So we've got the power, and that is a product of force and velocity, right? So that is, these are things that we need to calculate the power for. Apart from that, whenever you're talking about the efficiency, the very simple topics over here, whenever you guys are talking about the efficiency, remember that efficiency would always be either the output power upon the input power or the output work done upon the input work done. So these are the things that everybody should know. I'm pretty sure that you guys already know that about the efficiency, about the power, and about the conservation of energy. Now we've got the last topic in mechanics, and that is all about the law of conservation of momentum, right? And that is about the momentum. How would you talk about momentum in a layman words? G.
Product of mass
Well, everybody knows that it is going to be a product of
and
mass and
velocity.
velocity. J.
If you say
Product
it's an
of
amount
mass
of
and
energy
velocity.
to halt something.
Amount of?
Energy to put something at halt,
Mm,
in layman's words.
in layman words, I'm just going to talk about it like the intensity of collision, how energy is being transmitted, right? Intensity of collision. Before we talk about momentum, everybody needs to understand that what is an isolated system. Isolated system is when there are no influence of the external forces acting on a system. There are no external forces acting on a system. But for the questions, remember, we need to understand the law of conservation of momentum. Now, what type of questions examiner asks us from the law of conservation of momentum? The first type of questions are just the one-dimensional momentum. Got that? just the one-dimensional momentum. He's just going to tell us that we've got two balls, right? And they are moving towards each other. And after the collision, they're going to retrace somehow like this. He might be giving you the mass, this one, this one. He'll be giving you the initial velocity of this mass. He'll be giving you the initial velocity of this body. After that, he might get you guys the V2 as V1 as well, but he'll be asking you to calculate V2, right? These type of questions are very simple and they're just simple, the bet marks. But the only important thing that you guys need to consider, initially U1 and U2 are directly opposite to each other. So you need to make sure that you guys are using that opposite sort of a sign. Yani, if you're going to set up the conservation of momentum for these two masses, it must look like M1 U1 minus M2 U2, and that can be equated to M1 V1 minus M2 V2. Got that? Positive is for the balls moving to the right. Negative is for the balls moving to the left as well. At the end of the day, whatever V2 is, it could be positive, it could be negative, right? If it is positive, the ball should be moving to the right. If it is negative, the ball should be moving to the left. Got that, Ji? So one-dimensional momentum questions are very easy to tackle if you do know about the conservation of momentum. The problem comes whenever we've got two-dimensional momentum questions, right? When the body is not moving just along the horizontal, the body initially was moving horizontally, but right after the collision, the body started moving in another dimension, right? Got that? Now, for example, we've got some sort of an object over here. We've got an object over here, and it is right now in the state of rest, right? The mass of this ball is M1. The mass of this ball is M2. You've got U2 as 0, and you've got U1, and that, suppose, let it be 5 meters per second. Now, the ball gonna move to this mass, and right after the collision, the balls would not be moving in a straight path. Rather than that, the balls would start moving. One of the ball should start moving in this direction, and the other ball should start moving in this direction. Got that? And one of them is at an angle of 40 degrees, and the other one is at an angle theta. We do not know the theta. We do not know the V2. We do know the V1. For example, V1B, let it be 2 meters per second. Right? So these are the type of questions where students often mess up whenever it comes to law of conservation of momentum. Right? So how would you tackle such questions? First of all, just think about that you've got the initial momentum, right? If I'm talking about the initial momentum, it would just be 5m1 plus 0, because this ball is in the state of rest, right? So I've got the initial momentum, and that is just 5m1. 5 is for the velocity, right? But how would you guys calculate the final momentum of a system like this? Yeah. Which component of the motion is going to be effective in this case?
Horizontal.
Well, horizontal, right? So for example, you've got horizontal. For example, you are calculating the final momentum, and you're taking that horizontal momentum is effective. How would you calculate the horizontal moment? You need this component of the velocity. You need this component of the velocity, and you're good with that, right? How I'm going to do that? I've got this m1, the 2 meters per second. This component should be, cos 40. So the momentum of this ball, m1, gonna be somehow like 2m1 cos 40. Is that clear? Right? And the momentum of this ball is going to be something, because we do not know V2, right? We do not know V2, and we do not know theta as well. So the momentum of this ball is going to be, this was M2. It is going to be M2 times V2 cos theta. Just assume that you guys got M1 and M2, right? I can equate them up. I've got 5m1 is equals to 2m1 cos 40 plus m2 v2 cos theta as well, right? Okay. I've been telling you guys that we do know the masses, right? But now in the simple equation of the conservation of momentum, we've got two things unknown. We do not know v2. We do not know theta as well. And that is the point of this question. We cannot really solve this equation to get ourselves both the velocity and the angle theta. So how are we going to proceed from here, Jason?
You could take the vertical components. So you could take the sine components instead.
So, if we're going to take the sine components, what we're going to do with the initial ones? What we're going to do with the initial momentum? This one.
Would it be 0 because it's not
Exactly.
moving vertically?
Exactly. Brilliant. So what does that mean? That the initial horizontal component of the body, the initial vertical components of the body would have been 0 because this ball was moving in a straight line, right?
Yep.
Okay, so there was no vertical sort of a motion. But now, if you're talking about this sort of a motion, they can have some of the momentum in these opposite direction. So apart from this equation 1, I'll have another equation, and that would look like 0 to be the initial momentum. The momentum, the vertical momentum in this case is going to be something like m1 v1 sine 40. And for this one, I've got m2 v2 sine theta. What would be the sign between them? Jasmeet?
Can you repeat the question?
What would be the sign between them? Should we add them or should we, use a negative sign between them? Yeah.
I'm not sure.
Well, they should have been a negative sign because this ball is moving downwards, this ball is moving upwards, right?
Oh, okay.
So we do know m1, we do know v1, we do know m2, we do not know v2, and we do not know theta. And now I'm pretty sure that you guys can calculate, you guys can simultaneously solve these two equations to get yourself v2 and theta. Got that? If anybody want, I can explain this example again. Very important example.
Can you explain it again, please?
First of all, I've got two balls, right? This ball is in the state of rest, and this ball is moving towards this ball, right? In a straight line motion. The initial velocity of this ball was 5 meters per second, and the mass of this ball was m1. The mass of this ball is m2, and its initial velocity is 0. So the total initial momentum comes out to be 5m1. Got that? Now it comes to talk about that after the collision, the balls are not moving in a straight direction. Rather than that, one ball is moving over here, and the other ball is moving in this direction at these angles given. We've got 40 degrees over here, we've got theta over here. Got that? So now what I'm going to do, first of all, I'm going to calculate this initial momentum, and then I'm going to calculate the final momentums along the horizontal direction. I'm representing it with HF. So I've got 2m1 cos 40, I've got m2 v2 cos theta. How come we have got that? 2 was the velocity, and I'm talking about this component. So this should be 2 cos 40 multiplied by its mass, right? And then this one was m2. The velocity was v2, and I'm talking about this component. So this component should be v2 cos theta. And since they're moving in the same direction, I'm just using a plus sign. So this final momentum along the horizontal should be equal to this momentum along the horizontal as well, right? Initial momentum, and this comes out to be a final momentum. But this thing was that we've got a single equation, and we cannot really calculate v2 and theta from a single equation because m1, m2 were non, v2 and theta were supposed to be calculated. And from a single equation, I can't really do that. So then I took the perpendicular components of momentum. This ball would not be having perpendicular components. So initial momentum along the y-axis should be 0. Got that? I'm representing it with IY. Why it gonna be 0? Because the balls are really not going in a vertical direction. They're moving in a one dimension along the horizontal. Over here, I've got the vertical paths as well. So the vertical momentum is of m1 is going to be m1 v1 cos 40, where v1 is 2, right? And this momentum is going to be m2 v2 sine theta, right? I've got m2, but I do not have v2 and theta. And I'm going to equate it with 0. The sign between them should be negative because one of them is moving up, the other one is moving down. Got that? So after all these thingies, I can solve this equation and this equation simultaneously to get myself the final answer. Got that?
Yeah.
Yes.
Okay. Anybody else got some questions from it? Amy, Ahmed, Hassan, Ariba, Jason, Jasmeet,
Nah, I'm good.
Asad, Ahmed. Ji.
No, sir.
Okay, that's fine. So we're done with the mechanics now, right? And I've talked about some important types of questions that gonna appear in your exams, right? So conclusively, before we get to the materials now, conclusively remember that if you talk about mechanics, we've got some sort of a very regular pattern about the questions, right? In mechanics, whether I'm talking about the Cambridge or whether I'm talking about Edexcel, we've got questions from these topics every year. We need to know about the graphs. We need to know about the addition of forces, right? We need to know the principle of moments, right? Now, principle of moment both in 1D and 2D. Got that? Apart from that, we've got projectiles, very important. In projectiles, you need to understand that how can we calculate time, velocities, accelerations, blah, blah, blah. And then we've got the conservation of momentum. Conservation of momentum, the projectiles, the principle of moments, adding forces. Apart from that, at the end of the day, we've got the conservation of energy as well, right? So these are a few topics you'll get questions from, right? From the graphs, important question is that you need to understand the VT graph, the DT graph, AT graph, and how from the S and T square graph, you'll be able to calculate the gravitational acceleration, right? Very important 6-marker question. 3 markers for the Cambridge ones. And from how can you convert a distance time graph how can you convert a displacement time graph into an acceleration time graph, right? Whenever you talk about the addition of the forces, you guys need to understand that how can you draw the free body diagrams? Apart from that, how can you draw the scaled diagrams? And how can you add the non-perpendicular forces? How can you get the resultant of the non-perpendicular forces? We have talked about everything in this lesson. When you talk about principle of moment, if you're good with the resolution of forces, if you know how to resolve a force into components, you'll be able to attempt the 2-dimension principle of moment questions, right? So resolution is important for that. In projectiles, simple. You just need to apply the SUVAT equations for these questions. For the conservation of momentum, you need to understand how do we solve 1-dimension problems and how do we solve the 2-dimensional problems. Whenever you talk about the conservation of energy, you need to have some sort of a knowledge to set up an equation with respect to the given problem. Whether that given problem tells you about the potential energy, kinetic energy, elastic potential energy, blah, blah, blah. So over here, the equation is very subjective. You need to make up an equation every time for a different problem, right? So this was all we did in mechanics, right? If you've got any questions from these topics, you can ask. Otherwise, we'll get to the materials now. If you guys want to repeat that, recording would be available in a while. Okay. Okay. We'll get to materials now, right? So when you talk about the materials, the top most important questions are that we need to understand about the upthrust. We need to understand about the terminal velocity, right? And we need to understand the drag force as well. We'll get to these topics, but before that, we need to talk about a few basic things. We've got materials, right? And in materials, first of all, we're talking about the fluids, right? We've got 2 types of fluids, the laminar ones and what was the other one? The turbulent ones, right? How would you differentiate between a laminar and a turbulent flow? Ariba, important question for the Cambridge ones.
I don't understand the first one that you said. Could you please repeat that?
Well, I'm just asking you, how would you differentiate between a laminar flow and a turbulent flow of a fluid?
I'm pretty sure laminar is like where there's no mixing between any of the layers, and it's like the velocity is I guess you would say it's steady. and it's low at low speeds, whereas the turbulent is like obviously random, chaotic, I would say, constantly
Okay, but
changing
how would you
velocity.
write that down in the paper?
Laminar could have smooth, ordered motion,
Exactly.
and
Whenever you talk
turbulent
about the
would have
laminar flow, it
irregular
is some
motion.
sort of a steady flow of a fluid where every particle is just following the path of the precedent particle, the previous particle. When you talk about the turbulent
Yeah.
particle, it is an unsteady flow of the fluid where you're not following the path of the previous particles, right? So that is what we need to know about the laminar and the turbulent flow. Hassan, in which flow will get to have less friction, less air resistance, for example?
Less friction would be laminar.
Exactly. If we are talking about air resistance and we need less air resistance, the flow must be some sort of a laminar. It should be a steady sort of a flow. Got that? So laminar flow involves minimal mixing between the. ठीक है, sir. That's fine. Okay. So after talking about these fluids, we need to get back to the important topics. And we've got the upthrust first of all. For example, you've got this sort of a liquid, right? And we've got a person over here, right? Everybody knows that there must have been some sort of an upward force acting on it. How can you calculate that upward force, which is basically the upthrust? What would that upthrust be equal to? Yes, Jason?
Would the upthrust be equal to its volume and its weight as well?
Well, so upthrust would be equal to the volume of the body, right?
Yeah. And would it also be multiplied by its weight?
So volume multiplied by the weight.
No,
That wouldn't
That's
get
where
you
it's
that
density, no?
wouldn't get you the upthrust.
Upthrust is equal to rho Vg.
Exactly. The formula is rho GV. But how would you calculate the upthrust if you don't need to
Which is
use
just
this
energy.
formula?
Isn't it the volume of fluid displaced?
Well,
Wait,
do you think
it's
upthrust is a
volume.
force and you can equate it to the volume of something? Emmy,
It's the weight of the fluid.
weight of the fluid displaced, right? Or if I want to talk about the volume, it is the weight of the volume of fluid displaced. Got that? Did you guys get that? Right?
Yes.
Now, for example, I've got a foam of this size. At the same time, I've got a wood of this size, of the same size. They both got the same dimensions, right? What would be the upthrust acting on both of these things? This is some sort of a foam, and this is some sort of a wood. In which case, we'll be having more upthrust? Emmy? Wood. We will be having more upthrust for the wood, despite they both having the same volume. Ariba, would they be having would be having more upthrust?
No.
Well, they both should be having the same upthrust because they both got the same volume. So they'll be displacing the equal amount of the water, right? Okay. Everybody got that? Wood could sink deeper, whereas foam floats above. Exactly. And that is the main reason because they both, I never said that they both would be having the same weight. Foam and wood can have, they should be having different weights. But at the end of the day, both got different upthrust both got same upthrust because of their dimensions. Upthrust depends upon the volume, right? It has nothing to do with the weight. Wood would be having more weight, foam would be having less weight. So for example, if you've got the same upthrust, 5 newtons acting on the foam, 5 newtons acting on the wood, right? Wood has a weight of somehow like 10 newtons. Foam has a weight of something like 2 newtons. Which one of them is going to float? Absolutely the foam, right? Wood wouldn't be able to float. It would sink deeper. Got that? So remember that the upthrust depends upon the volume. It has nothing to do with the weight of an object you have immersed inside the water? If anybody got questions about this concept, you can ask. Mm-hmm. Okay, we're good to go now. So that is what we always talk about the upthrust. Upthrust is equal to the weight of the volume of the fluid that you have displaced, right? Not the weight of the object you have immersed inside the water. Got that? Now let's talk about the next thingy, and that is the terminal velocity, right? Ahmed, what is the terminal velocity? Hurry up, jaldi. No. What is the terminal velocity?
One by
Sir,
Yes.
what was the terminal velocity? Right.
Ahmed, are you watching TV as well with your
Sir,
lesson?
uh,
Which show you're
no,
watching?
sir. Sir, it's in the background.
Please do let us know about the show if it is, that enjoyable.
Sir, सबसे पहले बात वो terminal velocity is the maximum. Is terminal velocity was the maximum constant speed that constant speed of a falling object, where downward force of the gravity, downward force of the gravity and the upward drag force is acting on an object, which
Upward drag
results
force is acting
in
on the
zero.
object.
Which
Well, exactly.
results in zero
Whenever you talk
acceleration.
about the maximum, whenever you talk about the terminal velocity, it is a maximum constant velocity, but it is a velocity at the instant when the weight of an object falling through a liquid is equal to the drag plus the upthrust. Got that, Ji? Remember that whenever this condition is going to satisfy, your object would be moving with a constant velocity, having a maximum constant velocity, and that is going to be the terminal velocity. Is that clear?
yes.
Right. Now let's talk about the drag force. G, what is the drag force, Jasmeet?
Isn't it a bit like friction but inside a fluid,
Friction inside the fluid.
basically?
What would be the direction of that friction?
It would act opposite to the direction of movement.
Exactly, it would act opposite in the direction of the movement. And the main reason behind the drag forces is somehow the viscosity, right? If you're talking about a liquid, got that? Okay. So whenever you're talking about the viscosity, whenever you're talking about the drag force, that is mainly due to the viscosity of an object falling through a liquid. Got that? Now, well, we can calculate the upthrust by using this formula. Terminal velocity is a very generic thing, distance upon time, if your body is satisfying this condition. How would you calculate the drag force acting on an object? Jason?
Stokes law. Sorry.
Exactly. We're going to use the Stokes law. What was the Stokes law statement, Jason? What was it equals to?
Was it equal to 6 pi times the viscosity of the fluid times by the radius of, I think it was the object, and then that was multiplied by the velocity of the object.
Exactly. So the drag force is equals to 6 pi
eta
r vt, right? Good morning, Harry.
Hello.
Harry?
Good morning, Harry. I hope you had a sound. I hope you had a sound sleep.
No, sorry, my computer was working properly.
Okay, that's
Sure,
fine.
man. Just
I
excuses.
apologize. I apologize very much.
Okay, that's fine. No worries.
just
You've
playing.
got the drag force, and that is equal to 6 pi eta rvt, right? This is how we're going to calculate the drag force, right? And this is a statement given by the Stokes law. Now, a very important type of questions that we gets to, for example, we gets to get in Cambridge or even in Edexcel as well, that somehow we need to assess the validity of the Stokes law. We need to talk about the validity of the Stokes law, right? How can we assess that whether a Stokes law is being applicable on this sort of an object or not?
Stokes' law only applies to objects that are small, spherical.
Okay, these are the conditions. Stokes' law applies to an object having a small size. There must be some sort of spherical thingies, right? They must be flowing through a laminar flow. These are the preconditions, right? But mathematically speaking, what is the main condition for a body to be, completing all the conditions of the Stokes' law? That is that the weight of that object should be equal to the upthrust plus the drag. Got that? Right? For example, you've got this liquid over here, and you've got an object falling down over here. First of all, how would you calculate the weight of an object? Ariba, how would you calculate the weight of an object?
mg.
Well, remember, it is falling through a liquid, not through the air.
All right, so sorry, I'm sorry, you need to give me a sec.
Well, we can use that. We can use that. I was just asking you to justify it. We can calculate the weight by just using the mass of the solid times the gravitational acceleration, right? Body is still falling freely. It doesn't matter whether we've got air or we've got the fluid, right? Okay. So we've got the mass, we've got mass of the solid times the gravity, right? Upthrust, we can calculate it by just simply using rho g v, plus we can calculate the drag by just doing 6 pi eta r vt. Got that, Jim? That is how we can easily do that, right? Now, if you talk about this mass of the solid, how would you be able to calculate the mass of the solid if only the radius of this thing is given? You can just simply do, since density is mass upon volume, you can calculate the mass by just using d times v. So it comes out to be the density of the solid times the volume of the solid, which can be calculated by using 4 by 3 pi r cube times the g. Got that? Over here, we've got rho gv. This density is of the solid or the liquid, Jason?
Pardon?
Well, what this density refers to? Is it the density of a solid object falling down the liquid, or is it the density of an object or density of a liquid?
It's the density of the liquid.
Exactly, because we're talking about the upthrust, right? So density of the liquid times G times, again, this is the volume of the, of what thing, whenever you talk about this sort of a thing, volume of
spherical volume.
Exactly. 4 by 3 pi r cube plus 6 pi
4 by 3 pi
eta rvt. Got that? Now I can just simplify this thing down. I've got 4 by 3 pi r cube times g rho s equals to 4 by 3 pi r cube times the density of the liquid times g. This derivation is very important for the Edexcel ones. 6 pi eta rvt. Got that? So I've got all these things. If I want to assess the validity of the Stokes law, I just need to apply all the thingies in this equation. If both the sides are coming out to be equal, we're good with that. Okay. If not, then the Stokes law is not valid on a certain example given in the exam. But from here, I'll be calculating the terminal velocity because terminal velocity is important. So I'll make 6 pi eta rvt the subject, and this equation would look like 4 by 3 pi r cube g times rho s, take away 4 by 3 pi r cube density of the liquid times the g. Now I can further simplify this equation to make it look like 6 pi eta rvt equals to, I can factor out 4 by 3 pi r cube g from here, 4 by 3 pi r cube g from here, and that comes out to be density of the solid minus the density of the liquid. So the terminal velocity from here comes out to be 4 by 3 pi r cube g times density of the solid negative density of the liquid divided by 6 pi eta times the r. Got it? Pi gonna cancel out with pi, r gonna cancel out with its square, and eta would stay as it is. I've got 3 times 6 gonna be 18. I can further simplify this down. I've got 4 r square g times rho s minus rho l divided by 3 times 6, that's going to be 18 eta. Now I can simplify it further to have the final value for the terminal velocity, and that comes out to be 2r squared g times rho s minus rho liquid divided by 18 eta. So from this expression, you've got two conclusions, which would be helpful for the multiple choices in P1 of Cambridge, for the multiple choices of P2 for the 9 PHOs one, and for the unit 1 of WPH11. And what are those multiple choices? The terminal velocity is always proportional to the square of the radii. You can develop some sort of a relationship. And terminal velocity is inversely proportional to the viscosity, right? If Jason examiner is asking you about that, he's doubling the radii. He's doubling the radii of the falling object. How would the terminal velocity of an object be affected from that case? If he's doubling the radii, how many times terminal velocity is bound to increase or decrease?
Is it 4 times?
Exactly, because you've got r, so it's going to be 2r square, and 2 square going to be 4. So terminal velocity would increase by 4 times. Got that? Now, for example, if we talk about this sort of a thingy, well, coefficient of viscosity is mostly a constant. So this relationship only satisfies when you've got two different liquids. Got that? If you've got some sort of a liquid having a low viscosity, it would have, any sphere would have higher terminal velocity through it. Got that, Jim? So that is what we need to know about this sort of a thing, right? So important questions included the application of the Stokes law, right? Important for both Cambridge and Edexcel ones. This derivation is especially for the 9 PHOs and WPH Edexcels. This derivation don't really happen in Cambridge, but this relationship important for the Cambridge P1. Got that? So now, after that, we've got the last topic in materials, and that is all about the solid material properties. We've got the solid material properties. And whenever we talk about the solid material properties, the important thing is, first of all, include the Hooke's law. We have got the Hooke's law over here, right? Now, what does the Hooke's law tells us about all the times? Just meet.
Law is when the force acting on the object is proportional to the extension happening to the object.
Extension happen. Do you think extension can happen to an object?
Yeah, extension happens either, isn't it, because the temperature when it expands?
So F is somehow, in this case, when you talk about the Hooke's law, F is proportional to the negative X, right? In the Hooke's law. Ariba, what is this negative for? Why are we using a negative sign over here?
I would say, well, if X is for extension, I'm guessing negative means compression.
It's in the opposite direction to the equilibrium point.
Exactly. Right? And that is a certain name. It is known as a restoring force. Right? That negative is for a restoring force. It means that whenever you stretch an object by whatever force you want, if you haven't crossed the elastic limit, the object will always gets back to its original position. Got that? That is how we talk about the restoring force. Got that? So F is proportional to X. Got that?
I have a question.
G.
So F stays proportional to X given that the limit of proportionality is not exceeded, right? You said the elastic limit.
Elastic limit is not exceeded here. Somehow. Because there is a very minor difference, gap between the proportionality limit and the elastic limit. So we consider this statement to be true until, absolutely true until the proportional limit. But there are some questions when we need to get it till the elastic limit, right? But for the multiple choices, it is just the proportional limit. Got that? Did you get that?
Yes, I got it.
Okay. So F is proportional to negative X from here. And from this equation, you'll have somehow equals to negative kx. Now, from this equation, whenever you're going to draw an fx curve, it would always be a straight line, right? Until the proportional limit. So we'll have a straight line like this. How would you guys calculate the spring constant from this curve?
The gradient.
Exactly. The gradient would always gets you the spring constant. Very important multiple choice for P1s. What does the spring constant refers to? What does it tells us about, Jason? What does the spring constant tells us about?
Would the spring constant tell you how much the spring can stretch?
And what
Or
is the
the
perfect
rate?
name for that property?
Sorry, I don't know.
Well, that is the
Sorry.
stiffness, right? You were explaining it right,
Oh,
but that term is known as the stiffness. Got that? Ji? So the gradient of
yeah,
fx
thank you
curve
very
would
much.
always get you the spring constant. Now, if you talk about this curve and the area underneath this curve over here, that area would get you. Yeah, the area under this curve would get you.
Work done.
Work done. And that work
The
done would be equal to the elastic
half by
potential
fx.
energy, right? Okay. Jasmeet, how would you calculate the area under this curve?
Half base times height, basically.
Base is going to be x, height is going to be f. So you'll get half fx, right? Then you can even modify this formula because f is equals to kx. I'm just going to take the magnitude. So half kx times x going to be half kx square. Got that? So you can use this formula depending upon the circumstances. Got that, Ji? So this is what we need to know about the Hooke's law. Is that clear? Ji?
Yes.
Now, the next thing that we need to talk about are the mechanical properties of a solid, right? We have got the mechanical properties of a solid, right? And whenever you're talking about, you've got one important thing, and that is the stress. The next important thing is you need to know about the strain, and then we guys need to know about the modulus. Got it? So we've got strain, we've got stress, blah, blah, blah. Now, what is the stress? Apna, kya naam hai? Amit. What is stress? And how stress is different from a normal pressure?
Sir, can you repeat the question? My internet wasn't working correctly.
Okay, I'm just asking you about the stress. Force acting per unit cross-sectional area. That is fine, Ariba.
Sir,
Yes.
stress.
It is simply force acting per unit area, right? Okay.
Yes, stress is the
But
force acting per unit area.
exactly. But remember that whenever you talk about stress, it is a force acting per unit area to produce certain deformation. Is that clear? Whenever you
Yes.
talk about pressure, you've got the same formula. But in pressure, we never ought to produce deformation. Deformation is only about pressure. Got that, Ji? Now, secondly, whenever you talk about the strain, it is a measure of the change in the length or the volume or any sort of a dimension in the thingy. Now, remember that strain could be calculated in 3 different ways, right? You guys just know about the tensile strain, right? And tensile strain is just the change in the length of the wire to the original length. Whenever you talk about another type of a strain, remember that that could be the volumetric strain as well. Sometimes we need to calculate the volumetric strain. So the formula can be the change in volume to the original volume. Is that clear? Sometimes whenever you're talking about the lattice crystals of thingies, you can even calculate the shear strain as well. and that shear strain is just the tangent theta. So we need to remember all these formulas. That depends upon the problem. In most of the cases, both in Cambridge and Edexcel, we are supposed to be calculating tensile strain. But sometimes we can talk about volumetric strain. Sometimes we can even talk about shear strain. It is a change in the angle theta whenever you apply force on some sort of a crystal, and it deviates by a certain angle theta. Got that? Now, similarly, since we've got three different types of strain, we can even calculate modulus in three different ways. First one of them, everybody among us know it, and that is the elastic modulus. The second sort of a thing is the bulk modulus. The third sort of a thing is the shear modulus. The only difference is what strain you're talking about. For the elastic modulus, it is simply F upon A divided by change in length to original length. For the bulk modulus,
for the bulk and shear modulus, is that the Cambridge spec or the Edexcel spec?
Well, we've got a modulus in both the specifications, right? But there is a question in 8 PHOS actually in 2021 where you'll get to know about the volumetric strain. So we never know. We just need to know about strain, right? So your students need to understand that strain can be calculated in different ways. We can do tensile one, we can do the volumetric one, we can do the shear one as well at times. But in most of the cases, as I mentioned, he's just talking about the tensile strain. Right? Because he knows students are going to ask the same question. So F upon A upon delta V upon V, right? This could be the formula for the Young modulus. For the shear modulus, it is just F upon A upon the tangent theta. Got that? So these are the different formulas, but now the important thing is another point of view from the Hooke's law. Hooke's law, even though states that force is proportional to extension, but at the same time, there is another way to talk about Hooke's law, and that is that stress is proportional to the strain. And that makes sense, right? And from this formula, we can have stress equals to the Young modulus times the strain. And from here, Young modulus would always be equal to stress divided by the strain. Got that? Stress divided by the strain. So we've got this simple formula, but now, you know, the topic from where we get questions, and that is the graphical explanation of stress strain curve. So whenever we're talking about the stress strain curve, we've got, initially we all get a straight line, right? We've got, for example, stress over here. We've got strain over here, right? Initially, the graph is just a straight line, right? But there is a point where the stress and strain, or even F and X, are no more directly proportional. So the graph wouldn't be a straight line anymore. And what is that point known as?
Limit of proportionality.
Exactly. That point is known as the limit of proportionality, right? And then the graph, rather than going straight up, it deviates from the original path like this. And this point is the last point where the object can be elastic, right? Ariba, what is elastic? You know, what do we mean by an object to be elastic? What do we mean by an object to be elastic?
The object's elasticity, right?
Exactly. What do we mean by that?
So elasticity is like the ability of the material to return to original shape after the deformation is, I mean, the force is removed.
Exactly. So whenever you talk about that object is elastic, it means that the object can regain its original shape after the removal of the forces, right? Then after this point, the graph just move like this, right? This is going to be the UTS, or the ultimate tensile strength, right? And this point is going to be the fractured stress. Got that? Okay, ji? So you've got the UTS, you've got the elastic limit, you've got the limit of proportionality. Okay, for Cambridge students, this graph is very simple, right? You guys are often just asked to calculate the Young modulus from here, and you can do that quite easily by just calculating the gradient of stress strain curve up till the limit of proportionality. But coming to the Edexcel ones, he often asks one single question for a 3 or a 4 marker, that why in the stress strain curve, you can see even after achieving the ultimate tensile strength, your object is, fracture stress is a point where the object totally breaks down. Fracture stress is a point where the object totally breaks down. Why even after reaching the UTS, the body is breaking down at a lower value of stress? Permanent plastic deformation continued to stretch significantly even if load is removed. Amy, what are you answering? Oh, elastic limit. Got that. Ji, bacho. So I was, it was a question that why the object didn't break at UTS. Rather than that, the body is breaking at a lower stress, which is the fractured stress. Ji, why is that, Jason?
Sorry, I don't know.
Hassan?
Could you ask the question again?
Well, I'm just asking you that why stress at UTS is greater than the stress at the fracture of the solid?
Because UTS is the point at which the object is enduring the maximum stress.
The object is enduring
its maximum stress, and at the fracture stress, that maximum limit has been reached.
Exactly, and that that is the main question. That why the object is not breaking at UTS, right?
Because
it is not breaking at UTS. Rather than that, it breaks at a stress lower than the UTS. It is breaking at this point. Jasmeet?
Wouldn't it be something about prolonged exposure to the stress?
Exactly. Right? So basically, material breaks due to prolonged exposure to the stress, right? As soon as the UTS is achieved, the body is bound to crack, right? It is just a matter of time whether you get fracture at this point, 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 right?
Yes.
Okay. Now, apart from this question, we get another question. For example, up till here, this region, this is going to be an elastic region, right? If you guys are calculating the energy stored in the spring up till this region, that is going to be the elastic potential energy, right? Would you guys be able to calculate the energy in the plastic region? This is the plastic region, right?
No.
Well, we can,
Oh, yes,
if we've got certain number of boxes, right? We can estimate that, right, Hassan?
Yeah.
So you guys also need to you guys also need to know that we can calculate the energy in the plastic region by just estimating the energy per unit box. Did you get that? Now the last theoretical question, and often a 6-marker one, and that is ductile to brittle transition. That is about ductile to brittle transition. First of all, let me tell you that when what do we mean by a ductile object and what do we mean by a brittle object? Remember that any object breaking even before the elastic limit is known as a brittle, like glass, right? Glass is brittle. It can even break before even reaching its elastic limit. Ductile material is such a material which extends up till the fracture stress and then breaks down. Okay, so a material is ductile if it is reaching the fracture stress. A material is brittle if it is breaking even before the elastic limit. What is the reason for a certain ductile to brittle transition of the substances? Why do a ductile, how, in what cases a material can shift from a ductile behavior to a brittle behavior? Are there any conditions?
Wait, could you repeat that, please?
Well, I'm just asking you that a material can become brittle from a ductile, right? Did you guys understand what is the difference between a ductile and a brittle material?
Yeah.
Ductile is
Could you explain that again?
Ductile is a substance which goes up till the fracture stress, right? And brittle is a substance which can even develop some sort of cracks before the elastic limit as well, right? So I'm just asking you that in which cases a ductile material can transform into a brittle material.
When it gets really cold, when the temperatures drop.
Exactly. It is the sudden thermal change. Amy, how did the Titanic drown? That was the main reason, right? Somehow Titanic was floating along what was the ocean?
The Pacific.
Pacific. Was it Pacific?
I think that's wrong. Sorry.
Wasn't it
About the
Atlantic?
speculum.
It was Atlantic, right?
North Atlantic Ocean.
It was an Atlantic Ocean. So what
Yeah, no, the
happened in
Pacific.
the Atlantic Ocean when the Titanic somehow drowned?
It collided with an iceberg.
And what happens with an iceberg? The temperature dropped significantly, and the whole structure of Titanic, which was ductile, transformed into a brittle, and the whole ship just cracked into two pieces right after just striking a very tiny, what do we call it? The glacier or some sort of a thing, right?
Yeah.
Okay. So these are the type of questions, right? We get to, happen in the Edexcel and the Cambridge ones, right? So we're done with the materials now. And luckily I'm done. Yeah.
What is the relevance of temperature conditions?
Relevance of the temperature conditions, I didn't get that.
You said that the temperature dropped, which caused the fracture of the Titanic. But what does the temperature have to do with it?
Well, because for example, let's talk about the lattice. We're getting into the lattice structure of a solid now, right? What is the main reason behind the strength of a certain structure? It's molecules, right? How perfectly they're bonded together, how perfectly they're vibrating and responding to a certain amount of force being exerted on them, right?
Yeah.
Okay. It depends upon how perfectly they're bonded together. Now, for example, imagine the same molecular structure and the temperature in a second drop from like 5 degrees Celsius to negative 35 degrees Celsius. What would happen to that molecular structure? Don't you think molecules would stop vibrating?
They would.
Not stop vibrating, but somehow the amplitude of that vibration would decrease, right?
Of oscillations decreases. Yeah.
So when the amplitude of the oscillation, when the amplitude of the vibration is going to decrease, it means that the molecules are not going to behave in the similar fashion as they used to behave whenever an external force used to apply on that, right? So that is how, if the molecules are not responding to the external forces being applied, they can just simply, separate out and create some sort of a cleavage in the structure. Got that?
Yes.
Did you get that? Because the strength of a material comes from the bonding and the vibration of the molecules inside the structure. Is that clear?
Yeah. So it reduces it overcomes the force between the molecules.
Exactly.
Got it. Thank you.
So that is how a material turns from the, what do we call it? The ductile to a brittle. Very important 4 and a 6 marker question for the Edexcel ones, right? Acha. Now we'll talk about the type of questions we have come across in materials. These are the 6 topics that you need to prepare whenever you're talking about mechanics. Okay? I've written the subtopics as well. Now, as far as the materials are concerned, for both the Cambridge and the Edexcel students, you guys need to understand the validity of the Stokes law, that when it is valid to apply Stokes law on a certain substance. Got that? Right? And secondly, you guys need to understand the FX curves.
Yes.
Thirdly, we need to understand the stress strain curve. Stress strain curve and some sort of, you need to have a conceptual clarity of that curve, especially the stress strain one, right? You don't need to know just about proportional limit and the elastic limit. You guys need to go further beyond the ultimate tensile strength and the fractured stress. Got it? Okay. And apart from the last thing that we should talk about is the formula, right? We just got to know that Young modulus is equal to Fx upon A delta x. Got it? So from this formula, you can talk about the extension, how extension is related with all the other variables. Extension can be written as F times x upon A times the Young modulus. What does that mean? Extension is inversely proportional to the Young modulus. If a material got high Young modulus, it would be having less extension with the same amount of force. Got it? Apart from that, extension is inversely proportional to the area of the body as well. If your body got a lower diameter, it means that it is bound to have more extension. So these two relationships are also important for theoretical questions as well as the multiple choices you guys get to have in P1, P2 for both Cambridge and Edexcel. Got that?
Yes.
Okay. So that is how we need to talk about materials and mechanics. I've told you guys about these 4 types of questions we'll always have in materials. The most important one, if you guys need to understand, if you guys know how to manipulate this equation, that weight is equal to upthrust plus the drag, right? Every question is framed around the manipulation of this equation. Okay?
Yes.
Okay, so that was it for today. Now I'll take your questions. G, if you got any question from mechanics or materials, now you can ask. So we had Harry. Harry just happened to be here for about 10 or 15 minutes. Amy had to go get her
I
brother.
apologize for my next session. I'll be here the whole time.
Jason was almost here for almost an hour. Jasmeet was somehow here. Ahmed was watching a TV show. And Riva was praying.
Wow, very prayerful, mashallah.
Gee, and Amy didn't bless us with her voice as well. Okay, any questions from anyone?
Hassan, you must have some questions.
No, I'm good, man. I already know everything.
Okay, or everybody is asleep right now.
You sure, Hassan?
Yeah, I'm good, bro.
Okay.
Okay, then that's fine for today. I'll see you guys tomorrow at the same time for electricity and waves, right?
Yeah.
Okay.
All right.
Thank you very much.
Okay.
Thank you.
Thank you.
Thank you, Faran.
Thank you.
Sir.
Thank you. Thank you. Thank you.
Thank you. Bye bye.
Bye-bye.
Have a good day, sir.
Thank you. Bye-bye.
Khuda Hafiz.
Allah Hafiz.
Khuda Hafiz. Wait, I have a quick question before you go.
Yes, Gigi.
हम कल question करेंगे, or will it just be like today, mostly content and then some questions at the end?
Well, I think electricity and waves got a very huge content. So I framed some questions for you guys, but I wasn't able to do them because of the time we had. So I'll keep all the questions for day 3.
That's okay.
Right? If you guys got any questions
तो
from,
हाँ तो
you can bring them up.
जी तो संडे पे सारे क्वेश्चन पेपर सॉल्विंग है ना? ठीक है.
And
चलो.
how we're gonna write 6 markers as well. So I'm gonna let you guys know how we're gonna do that, right?
जी ठीक है.
Okay.
चलें, see you tomorrow same time.
Thank
खुदा
you.
हाफिज.
Allah Hafiz.
Bye.
Bye.
सर कल हम लोग यूनिट 2 का करेंगे ना?
हाँ जी, कल यूनिट 2 होगा. अहमद लेसन लिया था, सही हुआ था?
यस सर.
Okay then. I'll see you
सर
tomorrow
आप
now.
थोड़ा सा वो प्रोजेक्टाइल का ये प्रोजेक्टाइल मोशन के अंदर ये कौन से फॉर्मूलेज इस्तेमाल होते हैं सर? ये सर थोड़ा सा एक्सप्लेन.
SUVAT की equations, यानी V is equals to U plus AT, right? All these equations. Okay?
Okay, I'm just okay, clear sir.
Okay then. Bye.
Okay sir, thank you. Allah Hafiz.
Allah Hafiz.